Hello, in this video we find the differential of a function f of x. So here we go. I have two different functions here. They're written as y equals a function of x. So I'm going to do these examples and I'll try to explain a little bit what's going on. All right, so what we have is a formula for differentials, and this is a understanding of differentials from a first year calculus course. So this is not something that that you would see with a upper division or graduate level class. I mean, you'd see something much more. All right. So here's our formula for differentials. And so what we see is this guy here, f prime, and what we could think of this as is we can think of this as rate of change. Okay, that's derivative, rate of change. And then dx is a small change in x. Now, one way to think of the rate of change is maybe velocity. And this is something that we do all the time without thinking about calculus. We look at the rate of change being velocity. Say I'm going 60 miles per hour. I look down at the speedometer, 60 miles per hour. And then I look at how much time has elapsed, maybe an hour, and I think, okay, 60 miles per hour times 1 hour, that gives 60 miles. Now, this is called, this is an approximation, because when I do that calculation of 60 miles per hour times 1 hour, I'm assuming that the velocity is constant, and maybe it is. But the idea of this differential is that we for a moment assume that we assume that the rate is constant, and we evaluate the rate at a point here, in this case, x equals 3. You evaluate at x equals 3, and you find the rate of change at x equals 3. Now, as x changes by, in this case, 0.1, we assume throughout that interval over which it changes that the rate is constant. But for this function, the rate won't be constant. So but that's why it's a linear approximation. Okay, so let me write this as f, let's just find f prime. I mean, it becomes really just a question of taking the derivative. So this is even though it says y, we're gonna think of that as f. Okay, so it's x squared plus 2x. So for that polynomial, the derivative is 2x plus 2. And so we just get dy equals parentheses 2x plus 2 dx. It really is just following this formula and not becoming intimidated by trying to understand the meaning, although that's good, but it's a little bit not as easy to understand what's going on. See, the dy then is a small change in y along the tangent line. So now bringing in tangent lines, but it's a change. It's if we okay. So if we think of f, in this case x squared plus 2x, and we look at f and we think of it and we look at it very close to x equals 3. So if you go really close to x to 3, even though this is a curve, has some curve, if you go close enough, your curve sort of looks like a line and you approximate by a line. And then when you're looking at the line, if you're given a change in x, we can find the change in y by multiplying the rate of change, which would be the slope of the tangent line times the small change in x. I could bust out a big picture, but it's actually, that starts getting a little bit confusing. So I don't want to do that right here. Okay, then we're going to just go ahead and plug in these numbers. We have x equals 3, dx equals 0.1. So I would call this, if I have the formula, I would say that the part that might be difficult is, well, I don't want to just make a mistake on my, what I'm doing right now, multiplying and adding and so forth. But also the derivative might be sometimes tricky. In this case, well, it's a polynomial. So, okay, so that's the answer to that. So what it's saying is that when at x equals 3, if we change x by 0.1, so that means from 3 to 3.1, y changes about 0.8. It's an approximation. It's the rate of change times the change of x. The rate of change approximated to be constant when we put in x equals 3. Okay, let's go ahead and just do this one here. So dy, I'll write this is f prime again. But you could write dy dx, but anyway, f prime of x equals the derivative cosine x, which is negative sine x. And so then dy equals f prime of x dx. Okay, that's our formula. I'm just copying it down one more time. And so dy equals negative sine x. I think I'll use a parentheses times dx, so it looks a little neater and less confusing. Okay, and then I'm going to put in x equals 3, dx equals 0.1. Well, so 3 is, it's not a multiple of pi, but pi is around 3, so this is around, x is around pi. So anyway, dy equals negative sine 3. Well, I'll put parentheses here, times 0.1. So this is going to be negative 0.1 sine of 3 is dy. I just changed the order of the multiplication, so it might be a little clearer to understand. Alrighty, so I know I didn't write down a graph or whatever to explain this formula, but the differential formula, this differential formula is an approximation for a change of y when we assume that the rate of change is constant. So we evaluate the rate of change at 3, and the x changes by 0.1, and then we multiply rate of change. It's the same as miles per hour at an instant times the change in time, and you get the change in distance. But that's an approximation. If the miles per hour, if the velocity is changing, then over an interval, then it's an approximation. If I say, well, at the beginning of the interval, it's 60 miles per hour, but by the end of the interval, maybe 61. But anyway, you just take this 60 miles per hour, multiply by the change in time, get the change in distance. Okay, so that's all.